Have you ever held something made of titanium and wondered how a metal that feels so light can be so incredibly tough? From the wings of fighter jets to artificial hips inside the human body, titanium is everywhere, quietly shaping some of the most advanced technologies of our time. But this metal doesn't begin its life in sleek machines or luxury watches. Its story starts deep inside the earth, locked inside stubborn minerals that refuse to give up their secrets easily. Today, we're pulling back the curtain on one of the most challenging and fascinating metal-making journeys in modern industry, as we explore how raw titanium ore is transformed into one of the most extraordinary materials humans have ever engineered. Unlike metals such as copper or gold, titanium never appears in nature as shiny nuggets waiting to be picked up. Instead, it hides inside mineral compounds, tightly bonded to oxygen. The two most important titanium-bearing minerals are ilmenite and rutile, which are found in beach sands, river deposits, and ancient geological formations. Countries like Australia, South Africa, China, and Canada are among the leading producers, where enormous open-pit mines operate on a massive industrial scale. Giant excavators scoop dark mineral sands into trucks, which transport them to processing plants, where the ore is crushed, washed, and separated using magnets, gravity separation, and flotation systems. At this stage, the goal isn't to create titanium metal yet, it's to concentrate the titanium-rich minerals and remove as much unwanted rock as possible. Even though titanium is the 9th most abundant element in Earth's crust, extracting it is anything but easy. Its biggest challenge is ironically one of the reasons it's so useful. Titanium bonds extremely strongly with oxygen. That makes it naturally stable and corrosion-resistant, but also very hard to isolate into pure metal form. Early chemists tried and failed for decades to reduce titanium from its compounds without it instantly recombining with oxygen or nitrogen from the air. It wasn't until the mid-20th century that a breakthrough finally unlocked titanium's potential and allowed it to move from laboratory curiosity to industrial superstar. That breakthrough was the Kroll process, named after metallurgist William J. Kroll. Developed in the 1940s, this method remains the dominant process for producing titanium metal today. But instead of directly melting the ore, which would immediately contaminate the metal, the process first transforms titanium minerals into a different chemical form. The ore is heated in a reactor along with chlorine gas and a carbon source such as coke at temperatures of around 1000 degrees Celsius. In this extreme environment, the titanium reacts with chlorine to form titanium tetrachloride, a clear, volatile liquid better known in industry as TCl4. Meanwhile, many impurities such as iron stay behind as solid residues. Titanium tetrachloride may sound like just a stepping stone in the process, but it plays a crucial role. Because it is a liquid, it can be purified by distillation, allowing producers to separate it from trace elements like vanadium, silicon, or magnesium that would weaken the final metal. The result is a highly pure, yet dangerously reactive chemical. So reactive that when exposed to moist air, it forms a thick white smoke as it instantly reacts with water vapor. That's why the next step must take place in a carefully controlled, oxygen-free environment. Once purified, the titanium tetrachloride is transformed from a chemical fluid into solid metal through a reduction reaction. In most facilities, molten magnesium is used as the reducing agent. Inside a sealed reactor filled with inert gas or vacuum, the titanium tetrachloride vapor reacts with magnesium at temperatures of about 800–900 degrees Celsius. As the reaction proceeds, metallic titanium forms, but not as smooth, shiny chunks. Instead, it grows into a porous, brittle mass called titanium sponge. The byproduct, magnesium chloride, is later separated and recycled to recover the magnesium for reuse. The sponge may look fragile, but hidden within its rough texture is the birth of one of the strongest lightweight metals on the planet. However, titanium sponge in this crude form is unusable for airplanes, medical devices, or engineering components. To transform it into something structurally sound, it must be melted, purified again, and consolidated into solid ingots. This is usually done through vacuum arc remelting or electron beam melting, techniques that allow titanium to be melted without ever touching air. Even a tiny bit of oxygen or nitrogen contamination could embrittle the metal, so the entire process takes place inside massive vacuum chambers. The titanium sponge, sometimes combined with alloying elements like aluminum or vanadium, is compressed into large electrodes and slowly melted layer by layer into a cylindrical ingot. When the molten metal cools, it solidifies into a dense, uniform block, the foundation for every titanium product that will follow. But the journey doesn't stop there. These ingots move into huge industrial forges, rolling mills, and extrusion presses where they are reheated and reshaped into bars, plates, wires, or sheets. Each pass through the rollers refines the metal's microstructure, strengthening it and enhancing its mechanical performance. From here, titanium can begin its transformation into parts destined for hospitals, aircraft factories, sports equipment manufacturers, and high-tech laboratories around the world. One of the reasons titanium is so valuable is that it rarely remains in pure form. Instead, it is often blended into alloys that provide an even better balance of strength, flexibility, and durability. The most famous of these is T6Al4V, an alloy containing aluminum and vanadium that dominates aerospace and biomedical engineering. Aluminum improves titanium's ability to withstand high temperatures, while vanadium stabilizes its crystal structure, giving it remarkable fatigue resistance. This is the alloy used in aircraft landing gear, jet engine components, prosthetic joints, and high-performance bicycle frames. Other alloys incorporate elements like molybdenum, nickel, or tin, depending on whether engineers need extra corrosion resistance, heat tolerance, or toughness. Once titanium alloys are formed into their basic shapes, precision machining takes over. And machining titanium is no ordinary challenge. Because it retains heat and resists deformation, standard cutting tools can wear out quickly or crack under stress. Engineers must use specialized carbide or diamond-coated tools, slower cutting speeds, and flood cooling systems to control temperature. Every hole drilled, every edge milled, every surface polished must be handled carefully to avoid micro cracks that could weaken the metal in critical applications like aircraft wings or heart implants. After machining, many titanium parts undergo finishing treatments tailored to their purpose. Medical implants may be polished into mirror-smooth surfaces or textured to help bone tissue bond with them more effectively. Sporting equipment may be sandblasted or anodized to create colorful oxide layers that shift between blue, purple, and gold depending on the light. Aerospace components may receive heat treatments that refine their internal grain structure, making them stronger without adding extra weight. Each finishing step represents a careful balance between function, safety, and aesthetics. But as impressive as titanium is, its production raises serious environmental questions. Mining operations disturb landscapes, consume large amounts of energy, and generate industrial waste. The Kroll process itself is labor-intensive and energy-hungry, requiring high temperatures, chlorine handling systems, and extensive purification steps. That's one reason titanium remains expensive compared to aluminum or steel. Yet titanium's long lifespan and recyclability help offset some of that footprint. Once produced, titanium components can last for decades, resisting corrosion in seawater, chemicals, and even inside the human body. When they eventually reach the end of their service life, many titanium parts can be melted down and reused without significant loss of quality. In recent years, scientists and engineers have been searching for cleaner, more efficient alternatives to the Kroll process. One of the most promising is the FFC Cambridge process, which uses molten salt electrolysis to directly convert titanium oxide into metal. Instead of turning ore into titanium tetrachloride, this method bypasses several intermediate stages, potentially lowering energy consumption and waste. While still in development and not yet widely adopted, research into these emerging technologies hints at a future where titanium could become more affordable and environmentally sustainable. So why go through all this effort? Why mine vast mineral sands, refine chemical compounds, operate enormous vacuum furnaces, and engineer precise alloys, all for one metal? The answer lies in titanium's extraordinary combination of properties. It is as strong as some steels, but nearly half the weight. It does not rust in seawater, dissolve in the human body, or weaken under extreme temperatures the way many metals do. It stands firm in chemical plants, submarines, spacecraft, and inside living tissue. There are very few materials on Earth that can be machined into a jet turbine blade, implanted into a human spine, and crafted into a luxury timepiece. And titanium is one of them. Titanium also carries a unique visual and symbolic appeal. Its cool gray sheen suggests precision and modernity, while its subtle interference colors under anodizing give it an almost futuristic character. Whether it's the frame of a minimalist bicycle, the casing of a spacecraft instrument, or the ring on someone's finger, titanium represents more than just metal. It represents resilience, innovation, and the human determination to bend the most stubborn elements of nature to our imagination. From its beginnings as mineral grains buried in ancient sands to its final form inside rockets, airplanes, medical devices, and tools that push the boundaries of science, titanium's journey is a story of persistence, both in nature and in human engineering. It reminds us that the most remarkable materials in our world rarely start out remarkable. They become extraordinary through curiosity, experimentation, and relentless problem-solving. So the next time you see titanium, in a watch, a surgical implant, or the frame of an aircraft, take a moment to think about the incredible path it traveled. From oxygen-bound ore deep in the earth to high-tech applications that define modern civilization, titanium is more than just a strong metal. It is a testament to human ingenuity and a powerful symbol of how far we are willing to go to unlock the hidden potential of the world around us. Thank you for joining us on this journey through the making of titanium. If you have an idea for another material or everyday technology you'd like us to explore next, leave your suggestion in the comments below, and you might hear your name in a future episode. Don't forget to like, subscribe, and stay with us here as we continue uncovering the extraordinary stories hidden inside the objects that shape our lives.